So what we did in the basis, we want to now acquire a convergent beam pattern, and that will be interesting. It's something we align normally on the microscope, so I'm not very doing that very often on this kind of thing. So what we want to do is we want to use it, of course, remotely if we can. So we will only do a little bit of that. So as we did yesterday, so we updated our tile server yesterday, and there was a bug snagging in, which was fixed overnight. We have been running that for months now without a problem. So we are very inventive with putting bugs somewhere, but we also find them. So what we do is we open the column valve, and that does not work now because our camera is not in. Let's go back here, and you guys see that? No, we have no camera in here. Why is it not plotting? That is this weird bug of the new. So let's get an image diffraction pattern here. Here it is. It's a bit bright, and I guess we drilled a hole by now. It's interactive. Yeah. So we have a hole in our sample. Let's move it around a little bit. Where's my... Let's check it out on the main screen. Okay, so we see very nicely the hole we drilled. And now we see the, this is a bit, get things out of the way. Okay, a bit brighter maybe, so that you see that. So, and I will do some things that, we shouldn't normally be doing. So this is our center. It's silicon 110, so it's kind of square. Let's move to a different position. I want the thicker one so you see that better. So let's see here where we are. This is the same thing. I just want to zoom out some so that you see the sample. So it's a FIB sample. Why not zoom out all the way so we can see that nicely? 10 micrometer. So here's our FIB sample. And if I go a little bit to the thicker part, okay, can zoom in a bit. Okay. Without trying to do anything right now, just stop the scan. Ideally, we did not do that. And cannot make it any bigger here. We get our fourfold symmetry here of our crystal. Let's move it out by a degree. Let's be adventurous. And you can see, okay, we moved it downwards. And here now we can see this center. So the center of the beam is still here, obviously, but the crystal center is down there. And if we tilt it even more, right, we see our Kikuchi line, and we know this one is very thin, and so we should follow that one, and we go minus, and our center beam. I think we need a little bit less. So minus is upwards. We want to center it very nicely. Do you see the, so we have a little bit of drift here, so that's why this looks like it's alive. If we acquire the same diffraction pattern while we are scanning in a small area, let's try that. Just for, so we scan that, even though we are not in focus and we don't have atoms here. Let's go to a very small area, like 7 nanometer, just scan around and about. Okay, I should be more like Inspector Clouseau and make always new mistakes. Okay, so we see this pattern a little bit more clearly. And the reason is, with the scan, we change the, we destroy all kinds of coherence, and we get this pattern very nicely. And here we can see now extremely clear the four-fold symmetry. Four-fold symmetry you only can get. No, that is actually the HAADF detector is here. Okay, let's go back to a different contrast. So the probe forming aperture, so that is our convergence angle. Good question. And the high-angular dark field detector is there. And we can prove it's a high-angular dark field detector by, let's take it out, right? We want to, okay, view monitor 1. So I have 2 monitors now. So what we do is we take the high-angular dark field detector out. And now we have the full. Yes. So it's a 30 milliradian aperture, and you can see very nicely the higher order Laue reflections. So actually a ring. So it's here, right? And you see this ring much clearer when you do that with a convergent beam. Very easily, with you have very few spots in this higher order Laue zones that are within the excitation error. And when you have a whole variation of angles, and at some point or other, they will actually be exact, and you find very strong correlation. So actually we have here diffraction spots, and only the center ones have curved, have this excitation error 0. This is a very funny diffraction pattern, because this is a higher order Laue zone. So that angle depends now on as usually in the X and Y direction, but also on the Z direction. So it means you get a three-dimensional information from this diffraction pattern. So this is the higher order ones. Thanks for the question. I wouldn't have done that otherwise. We see our Kikuchi lines very nicely, right? So it's a star-like pattern. That's where we want to be at. What we don't see is the zero-order Lowry zone. And the reason is our convergence angle is actually too large. So we want to have a much smaller convergence angle. In order to do that, and I'm doing that because we will do 4D stems, so you will see a completely different diffraction pattern than what is here right now, and we want to get to that. So what do we need to do? I go to column and I put, that is funny. And I put a different, yeah, I killed the microscope overnight, so sorry. I had to reboot it. Things are a little bit funny. So we have here our small aperture. I can adjust it. I need my. Now let's leave that for the moment, because what we want to do now is we want to make the convergence angle a little bit smaller. And yeah, I need my virtual control, because here I need my Y. So it says here Y angle is. So you see everything is all over the place. And we are looking down here on the bottom for this convergence angle, okay? And that just makes this convergence angle small. And you can see now we have something very similar to a spot pattern. But what I want to do is I want to make that spot pattern so that we are just touching the disks are just touching. If I'm not sure you can see that at this point, but okay, it's not really perfectly in the zone axis. You'll figure that out later. Okay, I don't see that too well here. Normally I have it on a bigger screen. It's much easier to see. You see we are not perfectly in zone axis. You see here and here is bright. Here is bright, and this one is already in the first disk. So obviously left-right is not correct. I'll try to fix that a little bit here now with the stage. That is the wrong direction. Does everybody see that? So white line is in that, goes over there. So we want to go positive. Oh, that was perfect already. I'm glad I messed it up. So this is a bit closer. Let's look at these things in more detail. So I go to a different camera here. So it takes this. I have all this stuff in the way from. Okay. I see the camera. And the camera is not what I want. So I want a quarter and I want to have it big. Okay. And then here I can zoom in. There are a lot of features now in this convergent beam pattern, and the very obvious ones are the excitation errors, right? The excitation errors, I can probably do that a little bit. And do it slower. It's a little bit. Can adjust contrast a little bit here. We see a lot of features here. And if so, we see the center is a little bit off. We have different kind of black and white features. So this is our excitation error. We have a little bit more complicated excitation errors if we look at the diffracted beam. You see that? So again, we have a spot and something that's a bit off. So it's depending on where we are within the disk, we have a different excitation error. And because of the shape of this excitation error in the reciprocal lattice, we see that. The easiest way of looking at that kind of diffraction patterns is by looking at the symmetry, right? So this is obviously a square. And if we move that around, maybe my sample is a little bit bent. No, it's a bit unfortunate. With a bent sample, we could actually put that a bit closer to our to the center. If we try to do that, we have two different options. We can change the objective, the aperture itself and move that around. We can tilt it or we can tilt the sample. In this case, we already tilted the sample close to the zone axis, and we come to the question we had earlier. I thought you tilt the sample and not the beam. So in this case, we would want to try, we could try to do that on the with the sample, but we remember this is 8 milliradians, right? So we are already in the less than 0.1 degree range where we want to do that. So 10 milliradians, a hundredth of so it would be 1 degree about, right? And so we want to move it only a very small fraction of that. So we can try that. Since it's a summer school, so we try things out. Let's see whether we can do that. We need I did set on, yeah, okay. Okay, let's just try. we want to have set a little bit more to the, first we need a screen. Does it come? Yeah, I wanted not to do the camera length right now, so we'll handle that in a second. Yeah, so that is the other thing. We can move the aperture. Okay. Okay, let's, here's inserting. Okay, so finally. We first want to try to use the aperture, so we want to go a little bit more negative. Oh, its beam is retracted again. Okay, so we don't see anything. Let me double check where we are here. In an ideal case, we would have both screens here. That's what you normally have on the sample, right? Okay. So we want to try to move the beam a little bit to, okay, super. Okay. How good are we now? We check that. Take the screen out. We're a little bit better, still a bit up. And for that, we just move the aperture. Which we can also move. Let's try the other thing that was suggested here a second ago. That's what I wanted to do. So if we increase the camera length, so we go here to a larger view on the camera. The key thing is we will have a relatively small camera length when we do the 4D stem part. So we go in higher. Not sure how well that is aligned. So we have the largest. Miss. I'm so used to the other part. Get really rid of this thing here. Okay. First of all, we have now a diffraction shift on our part. I still have my column, so I undo this one. Go to the stage. Somehow I have still the condenser stick on mine. I want to have a diffraction shift. And now I need my. So you see, this is much easier when that is all automated. High contrast, it's a bit too high. Need my other one as well. This one should go away. So close enough for the moment. And to see what we would do with we can adjust that now. Again, we need we see that now we have the aperture X and Y drive. So we want to put it exactly on top of oh, shoot. Here we are. Okay, we want to put the aperture exactly in the center. So we center it on top of that. So we move it a little bit. So you see here, left, right. And this is too large. We are looking for the corners. Should be. No? It's not fine enough. Okay, so that is good enough for the moment. And we just can go back and acquire that on. No? Didn't we acquire that already? No. Yep. Not messing with it right now. So we go to the other one and just take an image. And we have very nicely aligned pattern. If we look at that, we see all the different features here are really in the fourfold symmetry independently. What we want to do next is, so remember how many black features we have here, how many squares we have here. By the way, if we look here closer, these spots we also will find and simulate them later when we go for the image simulation part, right? It really looks very round and Gaussian, like atoms, and we will find that that is actually really true. This kind of strange patterns that we have here okay, how do I get set nicely? Is also some things that we want to simulate. And so this is all due to our excitation error. So we have these two different parts here, two different stripes, and that is related to the thickness of the sample. So we have this kind of oscillatory behavior of the diameter of our excitation error with distance from the disk, and we will be able to hopefully match that as we go along. If we don't have a high-angle dark field detector in right now. So the problem is that we are not having a good image here probably because of our inner angle. So that's why I didn't want to change that for it's a question. Yeah. We could also tilt the beam. My beam tilt is not easily available. It's only available through the remote control. So let's go to a relatively large point here. Let's go down to the thin bit. We see here, not sure it's clear. So this one is considerably thinner than this one. And if we stop it, we see it is tilted. Let's see whether we get it somewhere in a. Okay. So there are a few thinner bits here. Just looking for one that is, no. Okay. So we will tilt that in this right zone axis here. Not to be in the middle. So it's just me, don't worry about it. Okay. So again, we can, getting smarter. Okay. So we want to tilt that sample over. This is a large tilt, relatively speaking. Minus is down, I think. That's very little that we're moving here. No, plus is down. So we see we are moving it down. We okay. It's the key thing. We go and acquire another one here. I should have acquired it. So we have a different thickness. So we have a different excitation errors, right? So we have only one of these black squares here anymore. And we get, depending on where we are in our sample, more or less of this. That must have moved because of this scan. So I should refresh that. Yep. So we move into the thick part. We have more. We have only a single white one. Can we get better? Okay. So barely one thickness fringe here. Again, we see the blobbiness of that pattern and how well these structures in the disks are related. If there's any kind of tetragonal, if there's any kind of tetragonal distortions, then you will see that immediately because the patterns will now not longer be the same left and right versus up and down. So you can actually directly look at these patterns and check that out. The thickness is directly related to how many dynamic diffractions you have, and we'll figure that out as we go along in today. So this is thin bits, thicker parts, thin and thicker ones. So we can check that and use that. If you want to do the whole thing together with the high-angular dark field detector, we go back to the, so we looked at the high-angular dark field detector before. Yeah. We have that here. So we have a lot of the Bragg reflections now on the high-angular dark field detector. In imaging mode, we'll talk a bit more about imaging. In imaging mode, you want to have only very high angles hitting the high-angular dark field detector, and so that you get contrast that is due to the atomic number square. If you increase the camera length, now we have basically a medium angle dark field detector image. So our image is not longer does not longer have the contrast that we would expect. The other problem that we have with this kind of conditions is that our Bragg spots do not overlap anymore. And the overlapping of the Bragg spots is actually what gives us our atomic resolution. So in the moment, we have very limited resolution, so we can try it. We have a lot of contrast on here. If you look at the, yeah, behind. So if you change the focus now and try to get that with a better resolution, I better do that on the image. Let's get rid of this one. We need to get to focus on something. We could focus on this dirt. That is actually no. Convenient thing to focus on is always say part from the FIB sample. Say okay. Maybe I get this to the side. It's in the way no matter what for me, so you don't see that. Okay. So we need to have a focus here. Let's look. Like I know which directions it goes here. Seem to be doing a lot. It's too much already. Yeah. Okay, here it comes. It's very slow. It's very far off. If you tilt, then you have a lot of. Should have done it with the C height, as I normally do that. We see the features in the top layer here. And if we zoom in now some more. No, doesn't like me. So, as I said, I'm not very. Is not high enough here. I think it's good. 10. And you're getting into the break, but the point is that with lower convergence angles, your atomic resolution is at some point disappearing, and that is usually at the point when, say, not longer overlap. So here we come a little bit more, and then it goes. So we probably also have a lot of astigmatism. Once you do these things, you have to realign your microscope. It goes it's slower, and people see that there is some amount of structure here, but it's not at the not longer at atomic resolution in the image. Maybe I lie. Okay. So the main point is you get information from the convergent beam patterns when they're not overlapping. And so you can actually go into in between. You want to have usually an image and a diffraction pattern. And so you have to make some kind of compromises. So that's the idea behind the whole thing here. So stops it here in the moment. It's a bit, as we saw, awkward. And we'll talk more about how to analyze this diffraction pattern. Well, we talk more about, it must be really off here. So we will talk more about how to analyze these diffraction patterns in the next lectures and after the coffee break of 10 minutes. Everybody? Okay.